here in chapter 6, we get to talk about discrete and continuous random variables. We're going to define what a random variable is here in a little bit. We're going to talk about what's the difference between what is discrete, what is continuous, and those two words have been in math pretty much since 7th grade. Okay, now whether your teachers talked about it, probably not. Okay, but those vocabulary words have been out there in your algebra-related classes. Starting in about the 7th grade. So we'll talk about what they are. We're going to go through practicing identifying if something is discrete or continuous. We're going to go through and graph discrete probability distributions, which means typically we're doing a dot plot or a histogram is what we're doing to graph. We're going to compute and interpret the mean of a discrete random variable. Then we get to do the same. Then we get to talk about the expected value, and then we get to talk about compute the standard deviations of these things. Now, some of them I'm going to show you how to do it by hand, but a lot of times we're going to use the calculator to our advantage to make things go a little bit quicker. Okay, here we go as we look at definitions. A random variable is a numerical measure of an outcome of a probability experiment. So its value is determined by chance. Random variables are typically denoted by capital letters such as X. So usually they'll define a random variable in saying like X is equal to the number of heads after a fair coin is flipped. So that's what, when they're talking about denoted by some capital letter, basically, more or less, it's just a notation. We're going to let some capital letter, whatever it is, equal some event. Okay, some random probability event here, experiment. And it's narrowed down. It's not a matter of, hey, heads and tails. It's just one thing. What's the probability of, I'm trying to think off the top of my head. I'm rolling a dice, rolling a 2. And I'm rolling the die 5 times. And so there's, we usually don't see a lot of cards in this situation, but we actually see a lot of extensions of this into real world scenarios with betting and gambling and that type of stuff. A discrete random variable has either a finite or countable number of values. The values of discrete random variables can be plotted on a number line with spaces between each point. So discrete means I'm not a decimal. I'm just a countable number. When we count on our fingers, it's like starting with our thumb. It's 1, 2, 3, 4, 5. All right. There was no 1, 2, 3 and a half, 3 3/4, and whatever. It's countable numbers. So discrete random variable means that my values are all physical, countable numbers going from 0 to whatever. No decimals. Okay. Now the next one, a continuous random variable. A continuous random variable, by definition, has infinite many values. The values of a continuous random variable can be plotted on a number line in an under-interactive fashion. So that one's talking about when we see an XY graph. And we see the graph plotted and it's got this nice little slope or whatever it is. We're using all the decimal places for the values and stuff. So when we look at, what are we're going to do some examples of discrete random variables in a second. Continuous random variables are typically like your measurements. Can you have a half? Can you have 3/4? Can you have 5/8? Can you have a 9 1,000ths and stuff? You're doing all the decimal places. That's what continuous is. You're doing all the little decimal places. Our examples of our scatter plots in the previous chapter, those are discrete. Each dot on a scatter plot was an ordered pair. Boom, done. Okay, we did not connect the dots. Okay, it was just flat out. We saw these dots. They showed a pattern. We did draw a least squares regression line, but we did not connect all the dots together. All right, so a scatter plot is an example of a discrete graph. All the other graphs that we did basically in Algebra 1 and Algebra 2, whether it's x squared, x cubed, those are continuous graphs. Because once you start drawing, you get all the little decimal places in between all the x values and y values. And that's why it's called continuous, because we're doing all the little places instead of just one order pair at a time. And we're skipping from order pair to order pair. So, as we scroll down, here we get to go through and decide which ones of these are continuous, which ones of these are discrete. Okay, so the number of light bulbs that burn out in the next week in a room with 20 bulbs. Is that a discrete or is it continuous? Yeah, it's discrete. It's discrete. Okay, I'm gonna do dis for discrete. The time it takes to fly from New York to LA. Yeah, continuous. Why?
Seconds, minutes.
Exactly. Perfect. We know it's hours, but it's also got minutes and seconds. Okay, so it's constantly changing until they actually take off and then sit and then touch down. The number of hits to a website in a day. Yeah, it'd be discrete. You either got on the site or you didn't. Okay, so there's no, hey, half thing there. The number of snow in Toronto during the winter. Yeah, continuous. Okay. The time it takes for a light bulb to burn out. Yeah, that is continuous because it's not always set to a set amount of hours. It is something that it could be the minutes and the seconds. The weight of a T-bone steak. Yeah, continuous. The number of free throw attempts before the first shot is made. Yeah, discrete. Okay. In a random sample of 20 people, the number of people with type A blood. Yeah, discrete. Okay. Again, if we keep the basic concept of can I include all the little decimal places? If I can, then it's continuous. If I can't, then it's discrete. Okay, that's what you got to keep in mind when you have to classify. All right. And that also lets us know when we look at procedures that we're learning in this chapter and the next couple chapters, it narrows down what kind of procedure we got to do. Okay, when we know that it's discrete or continuous. Okay, it starts saying, hey, we got to go towards this process. All right, the probability distribution of a discrete random variable x provides the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of a table, a graph, or a mathematical formula. A lot of times we see a table as the main focus, is what we see a lot of times for these probability distributions. We could see it as a graph. If it was a graph, I would probably say it's more of a looking like a scatter plot, or it's a dot plot, is what we see, is what it's displayed as. The mathematical formula, there are ones out there, but again, we're not going to see that for the most part in this chapter as what we're doing stuff with. We will typically see stuff as tables for the majority of what we're doing. So the rules for a discrete probability distribution. So and I have some tables down here below that we get to practice this on. So again, we're mainly see stuff listed like this is what we see it listed as. So the rules for you being able to say something is a valid probability model. First off, remember P of X stands for the probability of an event. If you don't, the shorthand, if you don't know it, this is the probability of event X. Okay, so whatever our random variable X is. So in the one I wrote up above, the probability of getting a hits. Okay, or having a head shown is what it should be. The probability of having a head shown in so many tosses. So first off, to be a valid probability model, each probability, each P of X inside that table has to be between 0 and 1. It has to be a number between 0 and 1. Can't be negative, can't be bigger than 1. Second thing, the sum of all those probabilities has to equal 1. So and we're going to practice it on the 3 tables here, and if you want to get ahead of me, you can. But we're going to practice to say, okay, are each one of these individually, are they a valid probability distribution? Okay? Are they a valid probability model? So the first thing we look at, are each of the values between 0 and 1? So as we look at the one on the left, that one's good, that one's good, that one's good, that one's good. Whoop, nope. We can't have a negative. Again, it's got to be between 0 and 1, and negative 0.07 is below 0. So I cannot, that is not, so we would say this first one is not a valid probability model. Then we go over here to the second one. I don't have to bother adding it up. Once I find one of the examples to where it's, hey, you're not between 0 and 1, I don't have to bother adding. On the next one here, I look at it and I say, all right, that's between 0 and 1, between 0 and 1, between 0 and 1, between 0 and 1, between 0 and 1. Fantastic. They're all between 0 and 1. So we met the first one. So we would say on the first one, yes, 0, p of x less than 1. So yes, we met that one. Now, what about the sum of the p of x's? So now I add. So 5, 9, 18, carry the 1. That's 5, 6, 7. Add 4 is 21. So that's 2.18. So we failed on this one because the sum did not equal 1. So we would say on this one again, not a valid. And I did I reverse stuff? Did I do bad math? There you go. Thank you, dear. I was thinking that was way too high. So not a valid probability model.
So it has to have both.
Yes. Can't be one. It has to have both. As soon as you fail one of them, you're not a valid probability model. Okay? And so that's why I would always check for, are you between 0 and 1 first? And then I would do the adding. Because I would not go straight to adding, because if we, I didn't add these up yet, but does that first one does that add up even with the negative 0.07? Does that add up to be 1? Yeah, so that's what happened. If you go straight to the adding, they add up to be 1, then you're like, hey, it's a valid probability model. Nah, because that one, we can't have negatives. Okay, so that's why I always test that one first. Is it between 0 and 1 every value? If so, then I do the adding of the column. Okay? Last one here. They all look visibly between 0 and 1. So on cause 1, we're good. On the second condition, 5, 9, 10, carry the 1, 5, 6, 7, and 10. Woohoo! Check. So this one is a valid model. Because we are good for both conditions. Now, this is where I got to put a little disclaimer. This is why we also, when we talk about decimal place values, how far do we go out? Sometimes when we only go out 1 or 2 decimal places, sometimes we'll be off on that second cause. When we add up the stuff, we may be just a little shy, like 0.99 or maybe 0.98, because we rounded different. Because the way we chose to round early, sometimes we're off a smidge. So that's why we go out the 4 decimal places, round to the 4th typically, because by then, when we start adding all this stuff up, we should be okay to be in that exactly 1. Okay. So that's the reason why we take a lot of stuff out to the 4th, the round to the 4th decimal, or some cases I saw some problems like to the 5th. Just because if we create these models, we're just trying to make sure that it does add up to 1 with the rounding parts. All right, graphing a discrete probability distribution. We're going to graph the discrete probability distribution and given, and then we're going to describe it. Okay, so with this in mind, we have to remember that these are percentages, this column right here. These are percents, or we can call them proportions. Sorry, proportions. So that would mean a histogram would be the best way to illustrate this. So as I look at my percentages, I go from 0.01 to 0.51. So I'm going to go 0.05. That's going to be a big one. That's going to, well, yeah, that's fine. That's 0.15, 2. Sorry, that's 2. 2.5, 3, 3.5, 4, 4.5, and then we got 5. Okay. So we don't have to go all the way up to 100% because we don't have anything up that high. So all I did was went up by, basically went every other line for 0.1 for a tenth. So now on the bottom, we would have our little categories. And then this would be my x values. So whatever my x values are for the random variable. And then we're just going to say, okay, 0 was 1%. So that's like just barely over the line. And then we had 10% for 1. And then for 2, we had 38%. So that puts us somewhere up about here. And again, typically when we're doing these models, you're going to be using a histogram for the majority of the part. The only time I would use a dot plot would be if they give me frequency counts. And then I would do dot plot for that if I wanted to. And then the last one, 51%, which gets me way up high here. Okay. Now, can we describe it? How would you describe the shape? Yeah, we would say skewed left. Again, anytime we graph from here on out, we need to make sure we're always thinking about describing it. What would we say about this? What would we say about the relationship between the mean and the median? Who's bigger if it's skewed left?
Median.
Why?
Because the mean is near the. Oh wait, no. The mean is bigger. Right?
Well, if
all the data is to the right, so there's more.
there is more data there, but okay, well, let's think about this one. We know the median always indicates what? 50% of the data is to the left and to the right? That's the basic definition of median, right? So with that in mind, if category 3 had 50% already, then that tells me that somewhere in 3 is where the median is 50%. And then to the left, so that would mean the mean would have to be below it. Okay, yes, it has more data, okay? Earlier on in the sections, we learned that when it's skewed left, basically whichever way it's skewed, the mean goes to that side. So since this is skewed left, that means that the mean is dragged to the tail, which means the mean is going to be smaller than the median. Whereas if it's skewed right, and we have a lot of small data and some big outliers to the right, and not as frequent, then the mean is bigger. Okay, so whatever way the tail goes, then that lets us know where the mean is. So the mean is always closer to the tail. So here we would say the median is bigger. Okay, so the median is bigger on this one. We can't tell if there's any outliers. We can say what the spread is. The spread is, what it is. But those are the main things we would be asking right now to describe the shape. All right. How do we compute the mean? We're going to do it by hand. That way, in case calculator dies and in case, you get a crazy teacher in the future that doesn't let you use the calculator or you forget. So the mean of a discrete random variable is given by the following formula. Mu sub x. Again, basically whatever they define the random variable is, that's the letter you're going to put down there for script purposes. Okay? So it is the sum. Again, if you didn't know what that Greek letter capital sigma is, that stands for sum. It means adding up all the stuff. Okay? So the mean of a discrete random variable is equal to the sum of every x value times its corresponding probability. And we have an example that we're going to do down here in a second. Okay, where x is the value of the random variable and p of x is the probability of observing it. How do we interpret it? And I left off a y there. If we perform many, many, many trials, we would expect the average, and then whatever our context of our x variable is, the average number of heads shown after tossing a coin to be about, boom, whatever that number is. So here's how you would go through and calculate it. First thing you would do is you would basically multiply across each thing. 0 times 0.01, 1 times 0.1, 2 times 0.38, and 3 times 0.51. That's the first part. You would multiply each of those together. So that would be 0.1, 0.76, and what is that, 1.53? And then now I add them up. I add up those answers. I add up what those things. What is the sum? What is 0 plus 0.1 plus 0.76 plus 1.53? And that gives me what it is. That's what the sum stands for. I add up all those answers. So that'd be 9, 13, carry the 1. Is that 2.39? Is that what you guys got by with the calculator? Out of curiosity? Okay, cool. So there is my expected value. All right, so my expected value, now we use a terminology, capital E of X is known as the expected value. That's the terminology, that's the function, the notation for it. And more or less, the expected value is equal to the mean, whatever the mean is. So in this case, our mean is 2.39. Again, those two words, expected value and mean, they are synonyms basically in statistics. So whenever you see the fancy terminology, they say, hey, what's the expected amount value of the profit? Like maybe in the next one here. What's the expected amount of profit? Expected value means mean. I do the mean calculation. And in this case, it's taking each individual event, multiplying it by the probability, and then adding up all those answers together. And that's the expected value. All right. So now I'll show you how to do it in the calculator. We'll do it in a few moments to make it go a little bit quicker. Because right now we're dealing with nice small tables. Sometimes they get a little bit more lengthier with maybe 5 or 10 or 15 numbers. So I'll show you how to do it in the calculator. Here's an example. A term life insurance policy will pay for a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose an 18-year-old male buys $250,000 one-year term life insurance policy for $350. According to the National Vital Statistics Report, the probability that a male will survive that year, the year is 99 or 0.998937. Compute the expected value of this policy to the insurance company. So what is it worth to the insurance company? Okay, so and from the insurance company side, we got to create a table. So as I create my little table with this, and we can just do 2 columns for right now. So we got our X in the first one and our P of X in the second one. And off to the side here, I'm going to write down live. And I apologize for being morbid. Dies. Okay? Because that's more or less what it is. We have a probability that the male is going to live. 99.89% chance that he's going to live that year when he buys this policy. Okay? So, first off, that's our first probability that we're going to stick in there. And then now, let's quickly find again, it's got to add up to be 100%. So what is 1 minus that decimal? Isn't it like 0.001063? If I did my subtraction right? Okay. So now we got to fill in the first part. Well, the first part is basically like the money. It is $350. Okay. The company is going to make $350 if this male lives that year. Okay. They made $350. Okay. And each year they renew the policy and the person lives that year, hey, they made $350, off of it. Now here's the challenge. Sometimes people die. Okay? Now, in relation to the company, when somebody dies and they have to pay out, what type of value is that number? Is it positive to the company or a negative? It's a negative. So now, what is $250,000 minus $350? Is it like negative 249, comma 650? Did I do my math right in my head? I'm hoping I did. All right, so now we go in to find the expected value. Now what we're going to do is we're going to multiply across 350 times 0.998937. And then we're going to multiply negative 249, 650 times the 0.001063. Now, the reason why we're going out so many decimal places is because it's money. It makes a big deal as we look at significant digits and figures as this company's looking at things as a whole when they write these policies and they do all the disclaimers and all that type of stuff. So, there are times when we use more because the dollar amounts matter on the big grand scheme of things. So as I try to get my TI calculator, and so there we go. So 350 times 0.998937. Again, I'm going to round at the very end. 349.62795. Now I do the next part, negative 249,650 times 0.001063. That looks good. Yeah. And then now I get to combine those together. So first answer plus the second answer equals 8425. So the expected value to the company is $84.25. That's what the overall expected value is. And again, that takes into account if the person dies. Obviously, the person lives. Hey, they made $350 and so forth. But what are they expecting? $84.25 is what they're expecting. Okay. So they did make a profit. It's just not a big profit off of this person. Okay. And it's not good to make a lot of profit off of a person's death anyway. That would just be like immoral. So, all right. How do we do standard deviation? The standard deviation of a discrete random variable x is given by the following equation. The square root of the sum of each x value minus the mean, square it, times the probability. So you'd have to go through, find the mean like we just did, that expected value, that 84.25. Take each number, 0, 1, 2, or there was two numbers. So it was 350 in the negative. We take each one of those, subtract the mean from them, square it to make it positive, then multiply them by the probabilities, add those two answers together, and then square root it. Now, not going to make you do that. Okay? Not going to make you do that. There's a lot of stuff. Okay? So what I did was to show on a problem what they were starting to do is they went through and said, all right, they had the mean here. They said the mean for this problem was like 2.39 for this one individual problem right here, that very first one of the examples we did. So they went through, found the mean, and then they said, all right, let me take each data value, subtract the mean from it, square it, times by the probability. We got these numbers. We add them up. Now, the only thing they haven't done is square root that thing right there. And that would be the standard deviation. That would be the standard deviation of x. So that's the only thing this screenshot didn't do yet. But they're showing like real quickly, okay, I take each value, subtract the mean from it, square it, multiply it by the probability of it happening, add up all those answers, then I got to square root it. So like for this one, the standard deviation, as I get my calculator again, would be the square root of 0.4979, which would give us approximately 0.7056. That would be the standard deviation of that probability distribution in that table right there. Okay. Now, granted, the insurance company one going to be different. Okay. Can I show you the faster way to do the insurance company one with the calculator? Because that's what I'd like to gravitate to, is show you the long way or the faster way. So let's get a table. So go into your table settings. So what we do when we're using the calculator to speed things up with it, L1 is going to be our first column, and then L2 is going to be the probabilities. So let's go ahead and put in 350. Oops, I forgot the 350. And yes, you got to put the negative in there. Negative 249,650. Now, and then in the second column, now it's okay. Right now mine has that E because it turned it into scientific notation, but that's okay. Don't freak out. Okay. So now we're going to go over and put in each of the decimals, and it'll probably put them in scientific notation. That's okay. It knows all the numbers. It just only has so many place values it can keep track of. 0.121063. All right, so it's got all those things in there. All right, so is everybody with me? Is anybody not with me as I type it? All right, we good? All right, now we're going to do a one var stat. Now we're going to do things a little different, so don't get ahead of me too quick. So we're going to get out of there, and we're going to go into one var stat. We leave L1 alone, so our list is still L1. Now in the frequency, we put L2. We put our probabilities here. So whatever column you put the probabilities in, that's what goes in for frequency list. So do second and then number 2. So that's what it's supposed to look like. Because what it's going to do for us is it's going to do all that, get the mean, subtract it from each data value, square it, multiply it by what's corresponding in L2 in that row, and then it's going to go ahead and add it up the square root of for us in a fraction of a second. So as I hit enter and get through this, there is our mean. Notice our mean, our X bar is 84.25. And then it only gives the standard deviation down below, 8146.5868. It will not give you a sample deviation here. I know that was part of the challenge in the previous topic. And, some of you did not read. I told you which one's sample or population, and some of you put the wrong one, and that's why you missed out. The Greek letter symbols are always population. Okay, the SX is the sample. Variance is not on the calculator. You got to do it by hand, and that's what some of you thought that the SX was variance. Variance is not SX. It is the standard deviation squared. Okay, so it's taking whatever the standard deviation is and raising it to the second power, because that's always the relationship. Okay, so that's where some of you, when we look at what did we miss in places, and as I give it back, that's where some of it was at. So there is our standard deviation. Again, if they want variance, put this in your notes. The variance in this case would be fat Rx squared. That's what the indicator would be as a symbol. That would be equal to 8146.586827, and then I got to square it. So you can go in there and say, all right, 8146.586827, raise it to the second power. Enter. My variance, fat Rx squared, equals 6631806.41. Thinking big number, 66 million. Okay. Now that just tells us the variation that's out there. And really, when we look at the grand scheme of things, we don't use variance a lot for describing the spread, but that's what technically it's calculated as. All right. Now there is a faster way that I showed you to get the variance so you don't have to type in all those numbers. Once you did a one var stat, if you pressed vars, go down to option 5, statistics, hit enter. Now we have basically option number 3 is your sample deviation, your SX. And then you have option number 4 is the fat RX. So we can just say, you know what, I want option 4, and then I want you to square it. And then I hit enter. Now, that one is a little bit different. Why? Well, I took the number that the calculator had, just the little digits that they had on it. Not all the extra significant digits. I only took the ones that was displayed. When I use this feature here, it's taking the, it remembers all infinite number of decimal places. And so when if I'm telling it to square an infinite number of decimal, that's why it's bigger. Okay? So you should be fine on Pearson just grabbing the one out of the calculator. Okay, you don't have to do this by hand doing this squared stuff. Okay, so I would say I think as I practice problems, the one var stat version would be fine for doing standard deviation, and you know they don't ask too many variance ones. So if you got a question and you're not curious, if the variance one pops up, let me know. All right, so let's get in here. We get to start. You know, how would we interpret it? You don't have a lot of interpreting problems, but we would say on average, the number of heads shown will differ from the mean, and we always specify what the mean is, and then we put the standard deviation is. So we always put whatever mu x is, whatever that value is, by about whatever the standard deviation value is. We always refer back to the mean as we talk about the interpretation of the standard deviation. Now we should be able to go in and we just got problems is all we're going to practice here for the rest of the class. Just different examples of are these valid, finding some of the probability stuff as we go through. I did put one on here on the life insurance because there's one on your homework. They did change the probability. And so forth. They also changed the dollar amount. So you want to do that one first while it's stuck on our head? You want to do that one? Skip down in your notes. Let's do that one there. Mr. Stevens stole your thunder. I forgot to delete my answer key. But let's see if we can work to that answer. Let's work to that answer. So as you create this, I would start with the probabilities first. So I would put the 0.999544 in that one. And then I would go 0.000456 in the second box. Sorry for the small boxes. I got to go back into Word and adjust that document. How much if they live? $200. And then how much if they die, unfortunately? To the company, 249,800, and it's a negative. And then again, I would do this in the calculator. Okay, if you want to practice doing it by hand, you can practice doing it by hand for the mean. But I'm going to just go ahead and go into the calculator, and I'm going to put them into L1 and L2 again. As I scroll down there and eventually get that back up here. Come on, there you go. So back in the stats, go into edit, clear out my 2 columns. All right, so it was $200, and then it was a negative 249,800, and then it was 0.999544. Oh, Mr. Stevens. Negative 249,800. Enter. Now 0.999544, and then 0.000456, and then I go stat, calculate one var stat. I got it set up with L1 and L2, and then I'm going to go through and go down to calculate. We found that the expected value The expected value is 86. Again, we matched there. What's the standard deviation? 5,337.3218. Again, you have at least one of those in this section's homework. Okay? So that's why I tried to put them on as extra examples in here so that, when you do it, because to me, those are the one that, typically we see like this type of problem with like gambling, like when you're going to a casino and they're talking about certain things pay out this much and so forth, or the odds of winning a raffle and stuff. At $5 a ticket, it pays out like 5,000. So that's usually the setting we see for these kind of these probability distribution tables is what we see as settings. All right, so let's go back up here. Again, you're always more than welcome to work ahead of me. I'm going to go back and we're going to start going through these. I'll ask some questions out loud, and then you guys can answer if you want to stay with me on it. So, in the Sullivan Statistics Survey, individuals were asked to disclose the number of televisions in their household. In the following probability distribution, the random variable X represents the number of households. Notice here, there's their definition. X is equal to the number of households. Verify this is a discrete probability distribution. All right, so first off, for part A, do we meet this case? Do we meet this case that each probability is between 0 and 1? Looking at it, looks good to me. All right, so yes, we met that case. Second case, is the sum of the probabilities, is it equal to 1? All right, let's see. 1, 2, 8, 14, 20, 30. So that's a 0, carry the 3, 9, 12, 19, 27, 28, 33, 35, 36, 37. Am I off on my math? Does it balance? Yeah, okay. I lost track of my digits, didn't I? All right, so yes, it balanced. Woohoo, check. Woo. So that's why we use a calculator when there's more than 3 things. All right, draw a graph for the probability distribution. Describe the shape. So again, since it's probabilities, we would go P of X on the left side. On the bottom, we got our X. And again, this one we got 0, 1, 2, 3, 4, 5, 6, 7, 8, and then 9. And then now it's just a matter of, okay, nothing for the first one. What do we get up to the highest as? 0.26. So, again, your choice on your scale. I'm going to go up by the 0.5s again. So we go 0.161, so that would be right about there. 2.61, so that's right about there. 1.76, so a little bit taller than that one. A little bit taller than that one. Back down to somewhere about there. 0.55, so that'd be somewhere about right there. Then we get smaller, so about halfway there. Then we get smaller. Then the next two are the same height, so let's go smaller. Boom, boom. So there is my distribution. And then they asked us to describe it. What would be a good description for that one? Yeah, I agree. Skewed right. Skewed right. Again, since it's skewed right, we would want to use the median as a descriptor about to describe the center. They're not asking that, but we would say that. We would try to figure out, okay, where is 50%? So where is the median? So what do those first 3 values add up to be? 8, 12, 19, carry the 1. All right, so somewhere somewhere, when I look at the median, that's 59% of the data in there. So somewhere right about here, somewhere between, somewhere around 2. So 2 to 3 is the median. Okay? Because again, median has 50% of the data to the left and 50% to the right. So the median is going to be somewhere around 2. Okay? Well, if we add up the first 2, we're a little bit short. So technically the median is probably like one of those values right in there. One of those occurrences in the small 3 area is where it's going to be. So determine the mean and standard deviation. All right, so let's go to our table. This is why I wanted to show you that calculator method quickly, so it kind of speeds these ones up a little bit faster. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, even if a variable has a 0, sorry, I got the 7 and the 8 star 78. We still have to show that x value of 0. If one of the x variables has a 0, we still include it because that takes effect into mainly the standard deviation aspect. May not add much into the mean aspect of the calculation, but in the standard deviation, it does have an impact. So we got to indicate, even if the probability of something is 0, we got to include it in our table. So on the next one, we get to put 0, 0.161, 0.261, 0.176, 0.186, 0.116, 0.055, 0.025, 0.010, and then 0.010. And then again, I'm going to go stats, calculate, 1 var stat. I got stuff set up into L1 and L2. And so again, my expected value, so my E of X, which is also equal to my mu X, as I go down here and press calculate, that is my 3.21. That's the expected value, or the mean. My standard deviation would be 1.7366. Now, how would we, it said to interpret, so let me write down an interpretation here. That way you have it in your notes. So let me get rid of the calculator. If we perform many trials, we would expect the average number of televisions. It's per household, right? Yes. Per household. To be about 3.21. And we can always put the units like televisions. I know you can't have 0.21 of a television, but hey, we got to include those decimals. So there's an interpretation about the mean. If we repeated this many times, we would expect the average number of televisions per household to be about 3.21 televisions. And then the standard deviation, as we try to interpret that, you don't have a lot of interpreting the standard deviation, but I like throwing it in there just because I for future we would say, on this case, we would say on average, the number of televisions per household will differ from the mean of, we state what it is, 3.21, by about 1.7366 televisions. Okay, so that's how you would interpret the standard deviation. Again, we don't have a lot of that, but in case it pops up for the final, I don't think there was a lot of interpreting the standard deviation in Pearson, but just in case on that university final, we just, we do it. Also, my AP kids, I try to keep the same terminology, that way it doesn't confuse me. They have to describe the mean and the standard deviation, so I try to use the same script in there. So, again, I'm going to start working on the next one. If you want to work ahead of me, you're more than welcome to do it. Ichiro hit parade in the 2004 season. You guys weren't even born when this happened. Ichiro of the Seattle Mariners set the record for the most hits in a season with a total of 262. In the following probability distribution, the random variable X represents the number of hits. So there they defined what X is. It's the number of hits Ichiro obtained in a game. Verify this discrete probability is a discrete probability distribution for the first part. So for part A, yes, each P of X is between 0 and 1, or you can just write down like this. And then that's the first one. And then second, I would need to add those up real quickly. I'm going to get a portable calculator instead of doing this split screen. We've got enough examples on the video for them to see the split screen doing stuff. So, all right, let's see. So, 0.1677 plus 0.3354 plus 0.2857 plus 0.1491 plus 0.0373 plus 0.0248. And that does equal 1. So the sum of the P of X does equal 1. Woo-hoo. So we're good. Does equal 1. So now they asked us to draw it. I figure you can draw a picture. All right. Again, we got the number of hits. We got P of X over here and the number of hits per game. And again, we have 0, 1, 2, 3, 4, 5. All right. And then we would draw some little picture there. Compute and interpret the standard deviation of the mean. So now I'm going to put those things in for L1 and L2 and do a 1 var stat. Where as I do my 1 var stat, in my list, that is L1, those are my X values, and then for the frequency, we're doing L2. Again, that's my P of X's. So let's get those in there. All right. Now again, if you got a question, flag me, okay? All right, so I got my stuff into L1 and L2. I'm going to do a 1 var stat. And I had frequency list, I'm going to put L2. And my expected value, which is my mean, is 1.6273 hits. And then my standard deviation would be 1.1785. Again, we would want to go through and interpret those, or at least interpret the mean is what they mainly asked you to do. They asked us some other follow-up questions here. What is the probability that random selected game Ichiro got 2 hits? Well, that would be, let's answer those real fast. Probability that he got 2 hits, 0.2857. And again, we would write that in script as the probability that x is equal to 2. That's how it would be written in script, in statistical script. Probability that x is equal to 2. And we would say 0.2857. What is the probability that in a random selected game, each row got more than one hit? Probability that x is more than. Does more than include 1? No, so we would just do greater than 1. So technically, as we looked at our last unit, we're adding up these 4 values. I could also use the complement rule. I can actually do the 1 minus the probability of x is less than or equal to 1, where I add up the 0 and which was 0.1677, and I add up the probability of 1 hit, because they said more than. So I can actually add up those 2 and subtract it from 1, and that'll be the same thing as adding up the 4 numbers. So it's really your choice if you want to just add up the 4 or if you just want to use the complement rule. So 1 minus the sum of 0.1677 plus 0.3354, and that is equal to 0.4969. So there is a 49.69% chance or probability that he's going to get more than 1 hit. Okay? Questions? Yes, dear.
Sorry, this goes back to the question earlier.
Yeah.
It asks like if it's in the hospital.
Oh, sure. Sorry, I'm said it. Let's go back to that. Because we always look at that. Would you consider this to be possible? Okay, so what is the probability? Oh, I didn't. Okay, so my apologies for skipping those other parts. What was E? 3 television was what? 0.176? 3 or 4 means I get to add. So that would be 0.176 plus 0.186, which is equal to carry that, be 6, carry that 0.362. What is the probability that a randomly selected household has no television? Probability, no TVs. No TVs would be basically probability that x equals 0, which is 0. Is that impossible? Did they say how many households they did? How many households they didn't tell us how many households. Okay. So is it impossible? No. It's not impossible. I know I do see some of these questions on here where they'll say, is it an unusual event? And usually 5% is, anything less than 5% is considered unusual. Okay? So their definition of the impossible, I mean, obviously if they got 0, that means they had a case come up that it was 0. Okay, like when they went through, they didn't tell us how many households they do. Usually they'll say they survey a random sample of like 20,000 houses, and they got this number of stuff out of it. Again, 5% as we look at tomorrow's topic and the other topic is usually what we use as a benchmark for is it unusual. Okay. In this case, for just today, I would say no, it's not impossible because they have an instance of nobody. They as they did their survey and they did it, nobody had 0 TVs. Okay. But as we progress through these random variables and these continuous random variables, then we're going to compare stuff to 5%. If it's less than 5%, then we consider it unusual. Later on in like our hypothesis testing, those chapters after spring break, we have 3 percentages we focus on, either 1%, 5%, or 10%. So then the situation will change based on those contexts of those problems. on whether we classify something as unusual or not. But for right now, we're going to use 5% starting tomorrow. And then for today, I would say no, it's not impossible.
So just because it's zero doesn't make it impossible.
Correct. Because again, it would be great if they gave us more information of how many people did this survey come across. And so they had so based on what they did, nobody said they had 0 TVs. Okay. Eventually, at some stage, we know there are some people that don't have TVs. Anybody have any relatives that don't have a TV? Out of curiosity. Okay. I mean, it is possible. A lot of times, it's the older grandparents and stuff. They're like, you know what? They don't want it and stuff, and that's the case. But in this small survey, we just have no clue. Just the sample, whoever they surveyed, nobody had 0 TVs. Okay. But eventually, we'll start seeing like a percentage when they start telling us out of like 50,000 people or random sample. So then we'll start using the comparing to 5%. Okay. So I'm gonna hit stop on the record button. The